In this video, we will discuss the concept of the reaction quotient. In our previous video on equilibrium constants, we had talked about how the equilibrium constant, capital K, is equal to the ratio of the concentration of the products raised to their respective coefficients that come from the balanced chemical equation divided by the concentrations of the reactants raised to their respective coefficients using the concentrations at equilibrium. The reaction quotient is the exact same ratio, except it's used when the concentrations are not at equilibrium. What we will be using the reaction quotient for is trying to determine which direction the reaction will proceed, towards the reactants or towards the products in its effort to reach equilibrium. So the reaction quotient is the value for the ratio of the concentration that we use to determine the equilibrium when the system is not at equilibrium. Essentially, it is the ratio of the products raised to their respective coefficients divided by the reactants raised to their respective coefficients when we are not at equilibrium. So at equilibrium, our value for Q, that ratio, is equal to the exact same value as K. The reaction quotient, we can use it to determine which direction the reaction needs to proceed to get to equilibrium. So if Q, our reaction quotient, is less than K, our equilibrium constant, that tells us that the denominator is too big. So our value on the bottom is too large, which pushes down the Q value. If our value on the bottom is too large, then the way that we make Q bigger is for the reaction to push to the right, to proceed to the right to make more products, more of the components that are in the numerator, which would make our Q value larger and have it move towards our K value. If, on the other hand, Q is too big, that means that the numerator is too big. So the value for the concentrations of our products are too large compared to the values for the concentration of our reactants. If we have too much product and not enough reactant, the reaction will proceed back to the left, forming more reactant and getting rid of some of the product to re-establish equilibrium. So if our Q is larger than our K, that means we have too many products, not enough reactants. The reaction will proceed to the left to make more reactants. If, however, Q is equal to K, that means that the system is at equilibrium, and the reaction will not push to the left or to the right. It will stay where it's at. Graphically, we can think of it like this. The red horizontal line represents our K value, and we're going to say for this particular process that the equilibrium constant is 1.45. The value for K can actually range quite a bit, but for this particular example, we're going to use 1.45. So if we go to a situation, and on our x-axis, these are the concentrations of A decreasing, which is our reactant, and the concentration of B increasing, which is our product, we're going to be graphing the ratio of B over A, which is our reaction quotient, right? The concentration of our products divided by the concentration of our reactants. If we're looking at a situation where our setup is completely in terms of reactants, everything is a reactant, we have no product concentration, so our concentration of the products is 0, our concentration of the reactants we will say is 1 molar. If we look at the ratio, that is 0 over 1, 0 over 1 is 0, so our Q is equal to 0. If our Q is equal to 0, it is going to be less than our K value. If the value is less than our K value, the reaction must proceed to the right to make the numerator larger, or you could think about it in terms of it needs to make more products. So if we have a Q value that is less than K, we need to make Q bigger. The way we make Q bigger is by increasing the value in the numerator, which is the products. So it will make more products, keep making more and more products until Q is equal to K. When Q is equal to K, the reaction stops proceeding towards the products and lays where it's at equilibrium. On the other hand, if we start in a situation where all of our molecules are in the form of the product and none are in the form of the reactant, We use the same ratio, products over reactants. So this time we have 1 molar for the product and 0 for the concentration of A, our reactant. 1 over 0 is infinity, which means that our value for Q is going to be bigger than K. Some K values can be very, very large, but they're not as big as infinity. So what that tells us is that because our Q value is bigger than K, our numerator is too big, our denominator is too small, and so we need the reaction to go back to the left to form more reactants to reestablish our equilibrium value. Our Q value is too big, it needs to go down. The way it will go down is by pushing the reaction to the left to make more reactants and remove some of our products. This is how we will be using Q to determine what types of things we will be doing in future problems. You will calculate Q, compare that to K, and that will tell you whether the reaction needs to shift to the left or shift to the right.